guess I'll try to run that anyway. I don't know why PowerPoint doesn't seem to want to do this anymore. Switch to manual override here. Audio music file. So not really a great tune. There we go. Rotation of Venus. That's what I wanted to.
It begins by showing the orientation of a reference marker.
Great. Fantastic video, but it's not going to work right now. There we go. So what we're seeing is just, again, this topographical map turned into a three-dimensional kind of rotating image. And again, you get the feeling that there are these continental-sized masses here and there. There's large basins with low elevations. Okay. So again, an object there is sort of like an Australia-sized, would be sort of an Australia-sized continent if we had actual water. That. All right, so we move on to the interior. Now, in the case of Venus, we have no seismological detections at all because even the Soviet Venera probe that landed on the surface, they knew they were going to die so quickly. There wasn't even any point in putting a seismometer on there because you'd have to be incredibly lucky to get a Venus quake in the few hours that this thing was actually going to survive. So a seismograph was not really a logical instrument to put on a spacecraft that you knew was not going to last very long on the surface. So ultimately, we have no direct evidence at all of the interior of Venus. But we can deduce a few things. We deduce that because Venus is a near twin to Earth, and yet it's a little closer to the Sun than the Earth is, well, it should be pretty fully differentiated, because even the Earth is pretty nearly fully differentiated with that massive iron core, right? Differentiation is the dense stuff sinking toward the center. Well, if you take a near twin to Earth and you put it even closer to the Sun, it should have stayed molten just as long, or maybe even longer, than the Earth. So we think that Venus is probably highly differentiated. We surmise that there's only one plate, just one single plate, not around a half a dozen plates like we see on the Earth, because of the lack of tectonic activity. It's probably a near twin to Earth in terms of composition, so the crust is probably silicon-rich, and the core is probably molten with a high nickel iron content. Now, one of the things we think about when we talk about planets is magnetic field. Is there a magnetic field? And how is it generated? And does it kind of fit the paradigm that we have for the production of magnetic fields? So remember, for magnetic fields, we basically need two things. We need some kind of electrically conducting fluid, and we need to churn it up with rotation, pretty fast rotation. Now, when we look at Venus, we believe that there's a molten core, so there's probably molten iron, which is electrically conductive, so that's criteria number one. But criteria number two would be pretty rapid spin. We don't have that in the case of Venus, because remember, it's got this weird, slow spin with a spin period that's over 200 of our days long. So Venus' spin is so slow, it's probably not exciting internal currents that are electrically conducting. And when we look at Venus, we see no magnetic field. So this actually fits the expected paradigm. It doesn't satisfy both of the conditions. It only satisfies one. There's a molten core, but it does not satisfy the criteria for rapid rotation. So the fact that we don't see a magnetic field is something we would expect. Right? When we look at the Earth, near twin to Venus, probably the interior is almost identical. We do see a magnetic field. And the difference is that Earth has this 24-hour rotation. I mean, over 100 times, over 200 times faster rotation than Venus has. So remember, there's an oddity there when we looked at Mercury, because Mercury actually does have a weak magnetic field, and yet it's also a slow rotator, just like Venus is. So when we look at Venus, we see no magnetic field, and that's consistent with the model. But when we look at Mercury, it's a little mysterious because we actually do see a weak magnetic field there. All right, so that finishes chapter 9, and we move on to chapter 10, talking about Mars. So a lot of people think of Mars as being the closest sibling that Earth has in our solar system. But actual fraternity analysis shows that Venus is the near twin to Earth, not really Mars. For one thing, Mars has practically no atmosphere compared to Earth, and it's also much smaller, only half Earth's radius, and only around a quarter Earth's mass. So it's more of a dwarf planet compared to Earth. It does actually have a thin atmosphere, but we're able to get a fantastic view of the surface because there's not too much atmosphere to get in the way. This particular photo, I believe, was taken with the Hubble Space Telescope, showing one of the hemispheres, one side of Mars, and there's the other side. We do see some unusual features, especially on this side of Mars when we look at it. So remember, if we had Earth on the same scale, it would be twice the size. So just keep in mind, this is a pretty much smaller planet than Earth is. But we see a gigantic valley there, which is sort of similar to Earth's Grand Canyon, but it's much larger. This is about 3,000 miles across. This is basically the stretch from San Francisco to New York, roughly. So it's a very, very large feature, but we're going to find that it's actually nothing like the Grand Canyon because it was not formed by water erosion, which the Grand Canyon was formed from the Colorado River flowing through it. This is actually a tectonic feature, the likes of which we have not seen on any other terrestrial planet. Over here, we see a few things that actually are things we also see on Earth. They're volcanoes. They're dormant volcanoes which went inactive millions of years ago. They were only active for a period of time when the interior of Mars was actually molten and had the convective currents that actually give you the upwelling that leads to volcanic activity. But even though they're dormant, they're still very notable because the largest of these is actually the largest volcano in the entire solar system that we know of. All right, so we're moving out into the area beyond the Earth for the first time in our solar system. Going from Venus at 0.72 astronomical units past the Earth to Mars, now 50% farther from the Sun than the Earth is. So we're kind of exploring this idea of the habitable zone, if you think about it. You know, everything's fine on Earth. We have life on Earth. We've seen that Venus is a little too close to the Sun. And it is kind of surprising if you look at that number. It's 72% of the distance of Earth from the Sun. And yet that makes all the difference in terms of habitability. It's too close. Mars is 50% farther out. You might think that's not that much of a difference. But again, this is going to turn out to be a little too far out. It's going to be too cold. So we really, by looking at these two planets, we can see that there's a pretty tightly defined habitable zone, right around 1 astronomical unit for a star like our Sun. All right, so looking at Mars's properties, again, we see it's about half the size of Earth. It's actually only about 10%, 11% of Earth's mass. And if we read across to the density figure, we notice for the first time a number for a terrestrial planet that's kind of on the low side. It's less than 4 grams per cubic centimeter. So remember that this average density figure that's in that final column is the one single number that best distills the composition and structure of the planet. It's one single number. When we look at these larger numbers for the terrestrials, the first thing we conclude is there's a lot of iron. There's got to be a lot of iron because if it's just made of silicate surface rocks, you're only going to see densities around 4 grams per cubic centimeter. So Venus, Earth, and Mercury clearly have a lot of iron. When we look at Mars for the first time, we're seeing the trend that occurs as we move through the solar system, which is towards lower density objects. Mars is actually kind of an intermediate planet. It doesn't have a lot of iron because it only has 3.95 grams per cubic centimeter density. Not a lot of iron, mainly silicate, actually kind of similar to the Moon's composition in that sense. Mostly silicate rock, not a lot of iron. And then if we go farther out to Jupiter, we see yet another massive drop in density by more than a factor of 3, just going from Mars to Jupiter. So one of the ways that we see differentiation in this course is actually not only when you look at one single planet, you know, like we look at the Earth and we see that most of the iron is at the core. So we call that differentiation because the definition of differentiation is when the dense stuff sinks to the center of gravitational attraction. But interestingly, we're actually seeing that differentiation phenomenon in the solar system itself because we're seeing the more dense planets closer to the sun. The less dense ones farther out. So differentiation is actually even occurring on a solar system-wide scale. All right, so this is a early historical photo of Mars. And when we look at Mars through telescopes, so kind of modest-sized telescopes, we do see features. We see features on the surface of Mars. And these features actually can change over time because of dust storms that can occur in the atmosphere. But they're pretty hazy-looking things, as you can see here. These, of course, are just very early Earth-based observations, not like the Hubble photos I was showing you a moment ago. Well, here we have Percival Lowell. He's actually not related to Schiaparelli, not a known alcoholic. So he was looking through the telescope and trying to understand what was on the surface of Mars. This is actually a telescope at the Naval Observatory in Arizona, which is pretty much a duplicate of the one that's in Washington, D.C., at the Naval Observatory in Washington. They bought two of these very large Allen Clark refractors, so you can see one just like this scope. This one's in Arizona, but we have one in D.C. very similar. There's Percival Lowell. He was fascinated with Mars. Now, he was actually observing in the pre-photographic era. I mean, forget about CCDs and iPhones and stuff. They didn't even have the capability to just take photographs with telescopes. So this is, 150 years ago. He's actually sketching things by hand that he sees. And you've got to always keep in mind that astronomers and scientists, they're just human beings, right? I mean, they're subject to all the foibles of human beings doing anything that they do. And amongst those foibles are the possibility to imagine that you're seeing something that might not really be there. And the other foible is to have an idea that you're really enamored of, which you're trying to push and prove, to be true. And when you combine those two things together, the idea that you could have an idea that you're fascinated by and you're interested in proving that right, with the idea that you can't really be sure what you're seeing anyway, you tend to get results like this, which are sketches that he thought represented evidence for life on Mars. He thought the linear features that he was seeing actually represented canals that were connecting different latitudes on Mars, so that he imagined an agricultural society on Mars where they're taking water from the polar regions and actually transferring it through canals to irrigate in the equatorial regions where the sun would be brighter. Just like on Earth, we'd have a higher sun on Mars in the equatorial regions. So this is a globe that he put together showing these, this fantasy of all these canals and things. Now, I got to say that Percival Lowell, that's actually a very well-respected astronomer and made lots of meaningful contributions to astronomy, but this particular one is one where he let his personal views sort of get in the way there. And when we get moved into the photographic era, we learn right away that there's no canals on Mars. You don't see them when you actually look photographically. They were only figments of his imagination. So this is another Earth-based shot of Mars where you can clearly see that there's a polar cap phenomenon there, and there are these weird blocky-looking things. In the Hubble era, we just don't see those anymore because the resolution of the Hubble is so high that you just see exactly what's going on, and you don't have this kind of sort of out of focus idea, which is what creates the possibility to imagine things. But blobs like this actually represent material moving through the atmosphere. There is a thin atmosphere, and it actually gives rise to dust storms, periodical seasonal dust storms. This is the first photo we're seeing today where you actually can get a hint of the presence of an atmosphere. If you look at the limb of the planet, which is what we mean by the limb is looking at the edge of the planet, you're looking through the thickest layer of atmosphere, right? Just like when we look at the sun at sunset, the sun's on the horizon, so we're looking through the thickest layer of Earth's atmosphere, and that's why we get the nice red sunset, because all the blue light is pretty much removed from the beam. Well, here we're looking at the limb of Mars, and so we're looking through the thickest layer of atmosphere, and you can see something. You can see there's a hazy atmosphere there. And you can also see some polar features there. This is actually another Hubble photo.